In this video, I am going to discuss another way that we can synthesize alcohols, and in particular, I'm going to look at the reduction of the carbonyl group. And so this can be used to synthesize primary and secondary alcohols, and we often use hydride reagents. And in particular, we use the sodium borohydride or lithium aluminum hydride, which are called complex hydrides, and that is in comparison to the sodium hydride and lithium hydride. And so we have these aluminum hydrides and borohydrides here rather than just having the hydride bound right to the cation. The lithium aluminum hydride is a stronger reducing agent, but it's more difficult to work with, but it can reduce more things such as esters and carboxylic acids, but it reacts explosively with water and alcohols. The sodium borohydride is much easier to work with and gives better yields, but it cannot reduce esters or carboxylic acids. And so if you wanted to reduce those, you would need to use the lithium aluminum hydride. So the mechanism that you would probably learn in a sophomore organic chemistry class would be something like this, where we have our borohydride right here, and so we can think of it as being in an equilibrium here with one of the hydrides coming off, and this hydride would come up here, attack the carbonyl carbon. Those electrons would move up to the oxygen, so we end up with this. We do a workup with water or acid, and so we end up just protonating that. And so that would be kind of the basic mechanism. So the real mechanism is a little bit more interesting, but it looks something like this. So this looks kind of like our hydroboration that we were doing with the alkenes. So the electrons from this bond, similar to what we saw above, are going to go to this carbon right here, and then the electrons from this bond will actually go to the boron there. So boron, remember, looks like this, and it has this empty p orbital here. So when it loses the electrons from that hydrogen bond, it opens up that p orbital there, so the electrons from this double bond to the oxygen on our carbonyl can then go to that empty p orbital on the boron. And so we end up with a transition state that looks like this, and the electrons will then move so that they are completely like this, so that we end up with our hydrogen bound to the carbon there, and then this boron here is bound to the oxygen. And so we do this then 3 more times so that we end up with 4 of these carbonyls bound to it. Then we do an acid workup and we end up with 4 of these alcohols right here. The ease of reduction for these, so aldehydes are the easiest to reduce. The sodium borohydride can reduce the aldehyde and the ketone, but if we want to do the ester or the acid, so the anionic version of the acid, we would have to use the lithium aluminum hydride. And so when we do the sodium borohydride, we do this, so we have the aldehyde here, and we are going to add a hydrogen onto the carbon and onto the oxygen up here, so that we get a primary alcohol, where with the ketone we end up getting a secondary alcohol. And if we do this on something that looks like this, so we have both a ketone and an ester here, and so the sodium borohydride, remember, will not reduce the ester, so we will just end up getting an alcohol ester here. And so if we want to do this with the lithium aluminum hydride, so we end up with the same thing if we did it on the ketone and on the aldehyde, but now we can do this on the ester and on the acid anion here. And so with the ester, we will end up with a primary alcohol. With the acid, so the carboxylic acid, we end up with a secondary alcohol when we use the lithium aluminum hydride. And so if we did this on our ketone ester here, we would end up reducing both the ketone, so to this secondary alcohol right here, and our ester to this primary alcohol right here. So another way to reduce our ketones is by hydrogenation, so catalytic hydrogenation. And the catalyst we will use is the Raney nickel. So this is a finely divided hydrogen-bearing form of nickel made by treating a nickel-aluminum alloy with a strong sodium hydroxide solution. The aluminum reacts to form hydrogen, leaving behind a finely divided nickel powder saturated with hydrogen, and this can be used to reduce ketones and aldehydes to alcohols. This will also reduce alkenes as well. So if we have something like this, so we have an alkene aldehyde, it's going to reduce both the alkene part and the aldehyde part, so the alkene will just become saturated here, and the aldehyde will become a primary alcohol. And we could do it with an alkene ketone. And so again, the alkene will just become saturated here, and the alcohol will become a secondary alcohol. So these are the ways to reduce carbonyls so that they become alcohols. And that was everything I wanted to talk about in this video. I hope you found it helpful, and I will see you in the next one.